In this chapter, we're going to be looking at extreme values. So those are maximum and minimum values of a function. So it's often important in applied contexts to be able to find where something has a maximum or a minimum. This is sometimes referred to as optimization. And so you can just imagine if the function is giving you the cost of a project subject to certain variables, then you want to minimize the cost. And if the function is telling you how much output you're going to get from a device, then you probably want to maximize the function. So anyways, so as we go to talk about this, we need to understand the difference between local and absolute, or I often call it local versus global. The book uses absolute, but I think in most non-mathematical contexts, they would say global. So let's see, so for this surface that I have right here, you can tell that there's the biggest value that the function attains is over here, up above the point 1, 0, the coordinate 1, 0. So here we would say that this is the absolute max of the function. And that's on this domain, so it's implied here that the domain is just what I'm showing you, so the unit square 0, 1 cross 0, 1. And so then this coordinate here, 1, 0, where the maximum occurs, that would be the maximizer. So the maximizer is the input value that does it, and the maximum itself is the output value at that location. If we look at where the minimum value of this function occurs, it occurs over here. So this would be the absolute minimum. And then the location just immediately underneath it there, that would be the minimizer. And then we also have what's called local max and min. So this point right here is what's called and actually here, let me get rid of that circle because I'm going to draw a disk in just a second. So that's a local min. And the reason why we call it a local minimum, and so if I just say draw the little line coming down to the point where it occurs, so there's the local minimizer, is that if I look in some little disk right here, I can find a little disk so that all of the function values in that disk are bigger than the dot I started with. And so if I map that, if I look at just the function values on this little red disk right here, it's going to let me highlight the region that it paints on the surface. Oh, sorry, that doesn't even show up. I'll just doodle it. Okay. They're going to get mapped into these values right here, and those are all bigger than the actual dot. A common way to visualize this is to think that if I were to actually take a copy of that little disk, and let's just make it blue for, well, how about yellow for contrast? Okay. So if I put it up here, like that, you can see that that disk lies entirely underneath the graph of the function. Okay, and so the way that we say that mathematically, we say that we have a local min, so there's a local min at some point A in the domain, so this is point in the domain. If and only if there's a disk centered at A of radius r with the function values bigger than at the center, and so this this notation right here, this is the ball of radius r centered at A. And if you want to get really fancy for it, the definition is that it's the set of all x's such that the distance from x to A, so that's the distance from x to A, is less than r. And it's B instead of, this is a B instead of a D because mathematicians call it a ball instead of a disk. That way we don't have to have a special word for each dimension. We just call everything a ball, even if it's like 1 or 0 dimensional. Okay, so there has to be a disk with that inequality. For all points on the disk. Okay, and so similarly, then we want to have the definition of a local max. A point is a local maximum if you put the little disk on it there, the value of the function is below it everywhere on that little disk. So if I drop a line down to the point in the domain that's mapping to that, then there we've got our little point over there. So maybe here, you can call these, so this is the point A1, and then we're looking at the ball at A1 of radius, I don't know, like 0.1 or something. And then over here, this will be our point A2, where the local minimizer is A2, and then B at A2 also radius 0.1, something like that. Okay, so that's the difference between local and absolute. And the difference between max and min is just that for a maximum, you would just reverse the inequality over here. And I didn't write it before, but I guess I could. There's an absolute minimum at some point in the domain if and only if f of x is at least equal to f of a for all points of the domain. Oh, that's probably a little more intuitive. Maxima and minima do not need to be isolated because we've got that non-strict inequality. So for example, let's take a look at this function right here. This looks like an exaggeration of maybe a vibrating speaker or circular membrane that's rippling. And in this case, we can see that the absolute maximum happens at this single peak right here. The absolute minimum value is going to be all the points around this circle. Each one of those is an absolute minimum. And then similarly, we've got local maxes. There's a local max at every point along the crest of this circle right here. And there's a local min that's not an absolute min everywhere around the bottom of this trough right down here.